Hey folks, if you're listening to this podcast or you read InfoQ.com, you'd probably like to keep up on the latest trends in software. I invite you to follow your curiosity at QCon San Francisco, November 18th to the 22nd, where you'll hear directly from engineers who will share how they implement innovations in real-world scenarios. Explore tracks like engineering productivity, programming languages and paradigms for the next decade, generative AI in production, and the signature architectures you've always wondered about, which I'll be hosting. Come learn from practicing senior software developers on how they are adopting emerging trends. Find out more about the conference at QConSF.com. We hope to see you there. Hi, everyone. Here at InfoQ, we try to provide our audience with information about the latest software innovations and trends. And I personally recognize that sometimes there's a lot of new information out there, and we tend to focus on the subjects that are most relevant to what we're currently working on and what we're interested in. Then sometimes you realize that what used to be one of those subjects off to the side is now right in front of you, and you can't ignore it anymore. And I'll admit that was my approach for a lot of the news over the past decade or so about big data, machine learning, artificial intelligence. I found it interesting, but because it wasn't what I was working with, I had this very thin, high-level understanding of most of those topics. And that's fine. That's how software architects usually approach a problem. We tend to be T-shaped in our knowledge. We have a broad range of subjects we need to know about, and we only go deep in our understanding of a few of them until we have to go deeper in our understanding for something else. So that's where I think we've gotten with ML and AI. It's no longer something off to the side. Architects have to deal with these every day. They're front and center because product owners, CTOs, CEOs, maybe even our customers are asking, can you put some AI in that? To just about everything, it seems. And that gets me to today's episode. I've invited Anthony Alford on to help explain some of these ML and AI concepts that are now, I think, required knowledge to be an effective software architect. Anthony's voice will probably sound familiar because he's another InfoQ editor. He co-hosts the Generally AI podcast with Roland Mertens, and I believe that just started its second season. So Anthony, thanks for joining me on my episode of the InfoQ podcast.
Thank you for having me.
So I think a useful way to go through this today in our discussion is to kind of do this big AI glossary. There's a lot of terms that get thrown around, and that's where I think architects need to understand what is that term and then figure out how much do I need to know about it so they can have intelligent conversations with their coworkers. I want to provide today just enough information so that those architects can go and have those conversations and realize when something comes up and they have to start implementing that for a project or thinking about it in design, they have a little bit more context, and that will help them be more successful to do more research. Sound like a plan?
Sounds great.
All right. So first, give me your definition of what is AI?
AI is artificial intelligence. So,
and we're done.
Yay. And in fact, when I talk to people about this, I say AI really tells you more about the difficulty of the problem you're trying to solve. It's not an actual solution. The good news is when most people are talking about AI, they're actually talking about some type of machine learning. And machine learning is definitely a technology. It's a well-studied, well-defined branch of science. And in fact, the part of machine learning that most people mean now is something called deep learning, which is also known as neural networks. And this has been around since the 1950s, so it's pretty widely studied.
Yeah, I think that's the idea that AI is not a product you can go buy. You can go buy a machine learning model. You can build a machine learning model. You can add it to your system, but you can't just say, I want an AI. Yeah. But that's the way people are talking about it. So let's start talking about the things that exist, the tangible elements. So give me some examples of what people are thinking when they say, I want AI in my system. What are the machine learning elements they're talking about?
Of course, most people are talking about something like a large language model or a generative AI. What I like to tell people as software developers, the way you can think about these things is it's a function. We write code that calls functions in external libraries all the time. That's at one level, you can think about it. It is just a function that you can call. The inputs and outputs are quite complex, right? The input might be an entire image or a podcast audio, and the output might also be something big like the transcript of the podcast or a summary.
And so that's where we get into most people are thinking of generated AI, Gen AI.
Right.
So give me some text, give me an image, give me some sound.
Right.
That's the input. And the machine learning model, it all comes down to ones and zeros, right? It's breaking that up into some sort of data it can understand and doing math on it, right?
Yes, that's right. And so again, when I talk to software developers, I say, when you think about the input and output of these functions, the input and output is just an array of floats. Right? And actually, it's possibly a multi-dimensional array. And so the abstract term for that is a tensor. And if you look at some of the common machine learning libraries, they're going to use the word tensor. It just means a multi-dimensional array. But you have to be able to express all your inputs and outputs as these tensors.
Yeah, these are the things I learned in math, like back in university years ago. But because I'm not a data scientist, I don't use those words every day and forget, oh yeah, a multidimensional array. I understand what that is. But
exactly,
that's like several extra syllables I don't need to say. So I've got these tensors I'm putting in. What do I do with it? How do I build one of these models?
Okay, so if you want to build your own model, which you actually might want to consider not doing that, but we can talk about that later. But in general, the way these models are built is a process called training and supervised learning. And what you really need, again, from our perspective as software developers, we need a suite of unit tests, a really big suite of unit tests, which means just what we expect. Some inputs to the function and expected outputs from the function. And the training process essentially is randomly writing a function. It starts with a random function and then just keeps fixing bugs in that function until the training to the unit tests pass somewhat. They don't actually have to exactly pass. You also tell it, here's a way to compute how bad the tests are failing, and just make that number smaller every time.
And that's where you get to the probability that this all comes down to math. So again, I'm used to writing unit tests, and I say my inputs are A and B, and I expect C to come out. You're saying, here's A and B, and I expect C, but here's how you can tell how close you are to C?
Exactly, yeah. It depends on the data type. I mentioned they all turn into tensors, but the easiest one is, let's say you're building a model that outputs an actual number. So maybe you're building a model that the inputs are things like the square feet of a house and the number of rooms, et cetera, and the output is the expected house price. So if you give it unit tests, you can get a measure of how off the unit test is just by subtracting the number that you get out from the number that you expect. So you can do sum of squared errors. Then the machine learning will just keep changing the function to make that sum of squared errors lower. With something like text or an image, it may be a little trickier to come up with a measurement of how off the unit tests are.
So we're getting into all the ideas of Gen AI. Let's just take the text example for now, and we'll leave off audio and images and everything else, because it's the same principles, but most people are familiar with interacting with ChatGPT. I type in something and it gives me a bunch of text. How did those come about? And how did we create these LLMs that people said, when I type in this sentence, I expect this sentence in response?
Okay, so how long of the story do you want here? So we can go back to 2017 or even earlier.
Let's give the high level details. If it's an important milestone that I think it's useful to sometimes have the origin story.
Right.
Origin.
So the short answer is, these things like ChatGPT are what are called language models. The input of the function is a sequence of words, or more abstractly, tokens. The output is all possible tokens along with their probability of being the next one. So let me give you an example. If I give you the input sequence once upon a, what's the next word?
I'm going to guess time.
Right. So what the LLM will give you is, will give you every possible word with its probability, and time will have a very high probability of being the next one. And then something like pancake would have a lower probability. So that's a probability distribution. We actually know the answer. So in training, we know that in the unit test, the word time has the probability of 100%, and every other word has a probability of 0. That's one probability distribution. The probability distribution it gives us is another one. And there's a measure of how different those are that's called cross entropy loss. So that's how you can train it to improve that. So it'll shift its output distribution to have time be closer to 100% and everything else 0. So that's a language model. And the method that I described is really how they're trained. You take a whole bunch of text and you take sequences of that text and you chop out a word or multiple words and you have it fill in those words. And the way it fills it in is it gives you a probability distribution for every possible word. And ideally, the one you chopped out has the highest probability.
Gotcha. So it's like the image recognitions that we've seen for years. We've had image recognition models. It's like, how do I identify this is a dog, this is a cat?
Right.
And we trained it. It's like, this is a cat, this is a dog. And it started putting that into its model somehow. It's like, when I see this array of pixels, the answer is such a probability that it is a dog in that picture.
Yeah. And in general, if we want to talk about data types, this is an enumeration. So with enumeration data types, this thing is what you might call a classifier. You were talking about a dog or a cat. It'll give you an answer for every possible output class. So every possible enumeration value has a probability associated with it. You want the real one to be close to 100%, and you want the rest of them to be close to 0. And it's the same for text. The entire vocabulary is given in a probability distribution.
And so that's when you hear about how big these models are, it's how much they've been trained on. The assumption is that ChatGPT and GPT-4 was basically trained on everything that you could possibly get off the internet. I don't know how true that is, but that's kind of the way people talk about it.
It's close enough to be true. So that's the data set. There's also the number of parameters that make up the model. So when we're talking about these deep learning models, those are neural networks. And neural networks are, at heart, matrix multiplication. I mentioned those input tensors. You could think of them as like matrices. You can multiply that times the model's matrix. So we talk about those matrix entries are sometimes called weights because ultimately what you're doing is a weighted sum of the input values. So when we talk about how big is the model, we're talking about how many matrix parameters are in that thing. For GPT-4, we don't know. We were not told. If you go all the way back to GPT-2, there was like 1.5 billion parameters in the matrices inside it.
Yeah, I think we're now seeing
hundreds of billions.
Hundreds of billions, yeah. So where does large language model come in? Is it in the billion?
Yeah, well, so it's not like a hard number. But what we're seeing now is if something is tens or hundreds of billions, that's probably large. We have smaller ones now where we'll see like Llama or something like, Gemma from Google and Phi from Microsoft. Those are still billions, but they're only, from 1 to 10 billion is considered a small model now. And that's small enough to run on your laptop, actually.
Okay, so you just threw out several other names, and these are the things that I'm talking about that architects are like, I think I've heard of Llama. Gemma sounds familiar, and what was it? Psi?
Phi. Phi, right? The Greek letter. Here in America, we Phi, but other places it's Phi.
Yep. And I know you can go out and find details of some of these. There's a site called Hugging Face that I don't understand, but you can go and find the models and you can test the models. Or what is that?
So Hugging Face, you can kind of think of as the GitHub for language models. And in fact, I mentioned the library. They have an SDK. They have a library, Python library you can install on your laptop that will behind the scenes download and run these smaller language models that you can actually run on your machine. And so what they do is they have files that contain those matrix entries that I mentioned.
And that's the composed model, if you will, right?
Mm-hmm.
Like I always think of this as the training is I'm going to run my program and the output is the model. So the training process might take hours or days, but once it's done, it's done and it's baked. And now I have the model, and now that model for large language models or small language models, you're saying it's something that I can put on my laptop. Some of those, if they were smaller machine learning models, we've been able to move those around for a while, right?
Oh, yeah. So we can think of 2 phases in the life cycle of machine learning model, the training that you mentioned. And so we could think of that as developing a function. And then once it's developed, once we've written the function, we might build it and deploy it as a jar, for example, or some kind of library that you can use. The trained model is like that. And when you load it up and you put an input into it and get an output out, that's called inference. So like the model infers some output from your input. And so those are the two big chunks of the model lifecycle.
Going back to the large language models, where you're talking about predict the next word and then predict the next word, this is where it's kind of feeding it back in. The way I've understood it is it's just autocomplete on steroids, that instead of one letter, one word, it's like, I'll just do all of it. And so it keeps feeding that sentence that it's building back into the context. And so that's the next thing.
That's right. And you'll hear these models referred to as auto-regressive. And that's exactly what they're doing. You start with initial input, which sometimes we call that the prompt. And we also call the input to the model the context. So the prompt is the initial context, and then it outputs one more token that's stuck on the end, and then it feeds back as the new context, and the process just repeats. These things also are able to output a token that basically says stop, and that's how they know to stop. Whereas I've tried that autocomplete with my phone, where I just keep autocompleting over and over. It eventually produces gibberish.
Yep.
But it is the exact same idea.
You've now said token a few times, and I keep saying word, and I know the layman is usually interchanging those, and it's not exactly the same thing, that a token is not a word all the time. What is a token in terms of these language models?
When people first started, it was words. We're probably familiar with the idea with search engines of doing things like stemming or things like that, where the word itself doesn't actually become the token. The reason you want to do something that's not exactly the word is, I mentioned, you can only get an output that is one of the tokens that it knows about. So you've seen things like, well, let's just use the bytes as tokens. I think now it's byte pairs. So basically, it's no longer at the word level. A token is smaller than a word. So you might see a token be a couple of letters or characters or bytes.
And so what's the advantage of shrinking those down? So instead of predicting the next word is once upon a time, it would predict T and then I and then M, then E.
Or something like that, or TI, or yeah. And the reason is so that you can output words that are not real words, that wouldn't be in the regular vocabulary.
Now, is it smart enough to say that time is one possible token and TI might be a different one? Does it break it down both ways?
So the tokenization that's almost become a commodity in itself. Most people are not really looking at, what the specific token data set is, but I think typically you want something a little bigger than one character, but you want something smaller than a word. So this is something that researchers have experimented with.
Yeah. And my interaction with knowing the number of tokens counts is when I've played around these things, used a ChatGPT or OpenAI API, it's measuring how many tokens are being used, and you're being sometimes billed by the number of tokens.
Yeah, that's right. Because essentially the output is a token, and the input we mentioned, that's called the context. The models have a maximum size of the context or input in the number of tokens. It's in the order of thousands or maybe even hundreds of thousands now with a lot of these models, but eventually it will have to stop because effectively you can't take a larger input.
Yeah, and I remember people found those limits when ChatGPT came out. Is you'd have this conversation that would go on and on and on, and pretty soon you watched the first part of your conversation just fall off the stack, if you will.
Yeah, the maximum context length is built into the model, and there's a problem with the algorithmic complexity is the square of that context size. So as you get bigger, the model gets bigger as the square of that, and that's how the runtime increases as the square of that, et cetera.
And so that's where you're getting into the efficiency of these models. There's been some discussion of how much power is being consumed in data centers all around the world to build these models, run these models. And that's one of those things that you can get your head around. Like if you have this thing that takes...
lot.
It's a lot. It's an awful lot. But if you have something that takes 30,000, 32,000 tokens, and you're saying the square of that, like that suddenly gets very, very large.
Oh, yeah. Not only does it grow as a square of that, but it's like there's a big multiplier as well. And training these models consumes so much power. Only the people who do it know how much, but really, they're just looking at their cloud bill. And nobody knows what the cloud bill was for training GPT-3 or 4, but it's a lot.
Yeah. So that's why people are looking not to build your own model. Most people are not in the business of needing to create their own LLM. These things are done, but people are using them to replace Google searches. And one of the problems is you don't have the context because the model wasn't trained on current events. It's not searching Google and giving you results. It's just predicting words.
Exactly. Now, they are trying to build that in. So if you use Bing, Bing is actually using GPT-4, and it will include search results in its answer, which when we get to I don't want to spoiler, but when we get to RAG, we can talk about that.
Well, let's leave RAG off to the side a little bit. Let's dig a little bit into Transformer without like rewriting the entire history. I think you and Roland have talked about that a little bit on your podcast.
Right. So we've mentioned LLMs and in general and GPT family in particular. Well, the T in GPT stands for Transformer. And this was something that a Google research team came up with in 2017. They wrote a paper called Attention is All You Need. They were working on translation. And, before that, the translation models were using recursion, which is different from what we were talking about with autoregression. But anyway, so they came up with this model that really just uses a feature called attention, or a mechanism called attention. And they called it the transformer. And so now really all the language models are based on this. And that's what the T in GPT stands for. GPT stands for generative pre-trained transformer. And they all use this attention mechanism. And you could think of attention as a way for the model to pick out what's important in that input sequence. The word is, I think, sometimes used it's similar to information retrieval. So it uses a lot of concepts like queries and keys and values. But at a high level, it's a way for the model to, given that input sequence, identify the important parts of it and use that to generate the next token.
So it might throw out some of your input or recategorize it and say, these are the important words in that context?
So the mathematics is, it finds the keys that match the query and then returns the values that are associated with those. And so a lot of times it does focus on certain parts of the input versus other pieces.
Well, that's where weighting comes into play, right?
Exactly. That's how it is.
You mentioned that these matrices have weights on them. And so it's going to figure out which words or parts of that input. And that one word doesn't always have the same weight. It's in the context of that input, it might have more weight.
Yeah, you did a better job explaining that than I did.
It's not my first time trying to explain this, so I get a little bit better every time. Again, one of the points of why I wanted to do this episode. So we've got transformers, just a term, and the attention, that's how we're figuring out what goes in. That outputs, in the case of GPT, it outputs GPT, but that's a branded term. LLM is the generic term, right? It's like Kleenex versus tissue. Let's say I want to use one of these LLMs in my application. This is the thing that my product owner, my CEO is like, put some AI on it. I want to look like we're being innovative. We've got to have something that is this predictive thing. Like, look at how it looked at our model and it comes up with something. How do we go about doing that?
Can I plug an InfoQ piece
Please.
Already? So just earlier this year, I edited the eMag, the Practical Applications of Generative AI e-magazine. And we had several experts on LLMs in particular talk about this. So definitely recommend everybody read that. But what they recommended is, you have publicly available commercial LLMs like GPT-4 or ChatGPT. There's also Claude. There's also Google's Gemini. AWS has some as well. Anyway, if you find one of these that seems to work, try it out. So you can quickly adopt LLM functionality by using one of these commercial ones. And it's just an API. It's a web-based API. And so you call it using an SDK, so it looks like any kind of web service. So that's number one. So number two, for long-term cost, maybe, right? So because it's a web service and an API, you're paying per, like we said, we're paying per token. It's actually probably pretty cheap. But longer term, there's cost concerns. And there may be privacy concerns because these commercial LLMs have gotten better at their promises about we're not going to keep your data. We're going to keep your data safe. But there's also the data that it gives you back. In the case of, say, like code generation, I think there was a lawsuit just recently, but I think that people whose code was used to train this, they're saying that this thing is outputting my code, right? So there's concerns about copyright violation. Anyway, longer term, if you want to bring that LLM capability in-house, you can use one of these open source models. You can run it on your own or in your own cloud, or you can run it in a public cloud, but on your own machine. And then you have more control over that.
Yeah, it's kind of the build versus buy model, right?
Exactly.
Like you can, and I like the idea of let's see if this is going to work. Do the experiments, run those tests on the public one, and maybe put some very tight guardrails to make sure you aren't sending private data. And I think it was, to plug another InfoQ thing, recently we had the AI ML trends report came out, and I listened to that podcast, and that was one where it mentioned that because they were setting up so many screens to filter and clean out the data before sending it to OpenAI or whichever API they were using, that scrubbed out some of the important context, and the results coming back weren't as good. Once you brought the model in-house and you could say, oh, we own the data, it never leaves our network, we'll send it everything, all of a sudden your quality goes up too.
Yeah, so it's definitely very easy to experiment with. And if you find that the experiment works, it may make sense to bring it in-house. So there's the short answer.
Yeah. Like you said, if you want to pay per use and it's easy to get started, that's one way to go. When you're talking about bringing it in-house, you mentioned you can have it on your own cloud, like we're on Azure, AWS. Is that basically I spin up an EC2 instance and I just install my own?
That's one way. Of course, the service providers like AWS are going to give you a value add version where they spin it up for you. And it's very much like the regular model where you pay per use. But yeah, you could do that. You could run it on EC2.
Yeah. Are you doing the product as a service, the platform as a service, the infrastructure as a service? Then you can do whatever you want on it. Mm-hmm. And so your results may vary, but that might be another way to do that next phase of your experiment as you're trying to figure out what this is. How easy is it for me to spin up something, put out a model there and say, okay, here's our results using this public API. And here's, if we bring it in-house with our private API, maybe look at the cost, maybe look at the quality of the results.
Yep, for sure.
So how are people comparing those things? What is the apples to apples comparison of I'm going to use OpenAI versus one of the things I pull off of Hugging Face?
So this is actually a problem. So as these things get better, it's kind of tricky to judge. So with your, in the olden days where we had things like linear regression and we had that supervised learning where we know the answer, we can get a metric that's based on something like accuracy, right? What is the total sum of squared error? But nowadays, how good is the output of ChatGPT? Well, if you're having it do your homework, if you get an A, then it was pretty good. And in fact, believe it or not, this is very much a common thing that they're doing now with these models is they're saying, we train this model, it can take the AP chemistry exam and make a passing grade. So another thing I see a lot in the literature is if they're comparing their model to a baseline model, they'll have both models produce the output from the same input and have human judges compare them. And it's sort of like a, Coke versus Pepsi, which, 4 out of 5 people chose Pepsi. And even more fun is do that, but with ChatGPT as the judge. And believe it or not, a lot of people are doing that as well. So I guess the answer is it's not easy.
Yeah. That's where I tend to say these things are non-deterministic. You talked about the probability. Like you don't know that the answer is going to come out. So your test is not, I asked this question, I got this answer, because you don't necessarily know what types of questions are going to be going in. So you don't know what outputs are going to come out.
Yeah, exactly. And that's actually one of the most scary things is you don't know what's going to come out. Something very unpleasant or embarrassing might come out. And that's really got people concerned about using these things in production environments.
Yeah.
But I will say one thing, again, talking back to my e-magazine, one of my experts said, before you adopt LLMs in your application, you should have good success criteria lined out for that. That may be the harder part to do. How will I know if it's successful? And it's going to depend on your application, but it's something you should think hard about.
Well, I like that because it puts back the question on the product owners, the CTOs. They're saying, I need some AI in it. What do you want to have happen? Because there's a lot of places where you shouldn't put AI. I work on an accounting system. You should not have it just guess your books. So when we're talking about using these for ourselves, whether we're hosting them or bringing them in-house, how do we get those better quality results? Do we just use them out of the box? I had a podcast a while ago and learned about retrieval-augmented generation. I hear Reg talked about a lot. Give me the high-level overview of what that is and why that should be a first step to make your LLM adoption better.
Yeah. So again, on my expert panel, they said the first thing is to try better prompts. So we've probably heard of prompt engineering. So we know that the way you phrase something to ChatGPT makes a big difference in how it responds. So definitely try doing stuff with prompts. The next step, retrieval-augmented generation, or RAG. I think we mentioned the LLMs, they're trained and they don't know anything that happened after that training. So if we ask, who won the football game last night, it doesn't know. Or it might not say it doesn't know. It might actually make up something completely not true. Well, this is also a problem for a business where you want it to know about your internal knowledge base, right? If you want it to know things that are on your wiki or in your documentation, things like that. What RAG is you take your documents, you break them up into chunks, but essentially you take a big chunk of text and you run it through an LLM that generates a single vector for that chunk of text. This is called an embedding. And that vector in some way encodes the meaning of that text. So you do this with all your documents, and then you have a database where each document has a vector associated with it that tells you something about its meaning. Then when you go and ask the LLM a question, you do the same thing. You take your question and you turn that into a vector. And the vector database lets you quickly and efficiently find vectors that are close to that and therefore are close to your question in meaning. It takes the content from that and shoves that into the LLM context along with your question. And now it knows all that stuff along with your question. And we know that these LLMs are very good at, if you give it a chunk of text and say, explain this, or here's a question about this chunk of text, it is quite good. That's what the intention mechanism does, is it lets it find parts of that chunk of text that answer the question or solve the problem that you're asking.
The way I've heard that explained is, let's say I do my search, and instead of me writing a really elaborate prompt, because I'm only going to sit there and type for 30 seconds, and that's all the words I'm going to come up with. Instead, I would say, answer the question based on these documents, and I can give all those documents in the context, and now it knows, okay, that's what I'm going to use. I'm not going to use just my base level LLM predict the next word. I'm going to predict the next word based on this context.
Right. And the retrieval part is finding those documents automatically and including them in the context for you. That's the key component, is because if you actually know the documents, and let's say somebody gave you, here's our user manual, answer questions about it, which is a pretty cool use case for someone who's, say, in customer service. If the user manual is small enough to fit into the context, which it probably is at hundreds of thousands of tokens, then that's great. But maybe you don't have that. Maybe you have a bunch of knowledge base articles. And so this will go and find the right knowledge base article and then answer the question based on that.
Right. Because our knowledge base has tens of thousands of articles opposed to, a couple hundred pages.
Exactly.
So,
yeah.
And you're still using the LLM, which has all of its knowledge of, here's how I complete a sentence.
Yep.
You are not building a new model based off of your knowledge base or your training documents.
Exactly. But let's say you did want to do that, and that might be a better solution in some cases. This process is called fine tuning. So I mentioned the T in GPT was transformer. The P is pre-trained. This is a whole subfield of machine learning called transfer learning, where you train a model, so you pre-train it and its general purpose, then you can fine tune it for a specific case. In the case of GPT 2, 3, and higher, they found out you kind of don't need to. It's pretty good on its own. But what the fine tuning does is it's additional training on that model. So instead of using the model as is, you restart the training process. You've got your own set of unit tests. So you've got your own fine tuning data where you know the inputs, you know the outputs. The advantage is for fine tuning, it can be much smaller than what is needed to train the full GPT.
And that's because you're starting from what already exists. You're not starting from a baseline of nothing. And it's just saying, tweak your model. And that's going back to things that I understood, again, at a superficial level with machine learning training, is that you can overtrain the data. Like if you give too many answers in one area, it's like, look, we got to a 99.9%, but then something comes in that it doesn't know about and it has no answer. It's way off base. In this case, if I'm trying to get the model to be very specific to my company's applications, my data, that might be the desired outcome. I don't want someone to be using my customer service chatbot to ask about when's the next Taylor Swift show.
Yeah, exactly. And in fact, so ChatGPT, the original ChatGPT and newer models, they do fine tune them to give more helpful answers and follow instructions. So this is something with GPT 3.5. Again, that model was pre-trained on basically the whole internet, and it could give you answers that were pretty good, but they found that sometimes it would just give you answers that were, it's that whole joke about this is technically true, but not at all useful. So they fine-tuned it to give you answers that are more helpful, to follow instructions. They call it alignment. And the way they do that is they have a small data set of, this was the input, here's the output you gave, but this output here is better. And so they fine-tune it to work towards the more appropriate output.
I need to back up just a little bit. When you mentioned we're going to create these vectors, I'm going to have a vector database, I'm going to do a vector search. Another one of those terms that gets thrown around, and people are like, well, do I have a vector database? I think Azure just announced that they're going to, I think it's in beta right now, basically turn your Cosmos database into a vector database, like flip a checkbox in the portal and all of a sudden you have vectors. What does that do for me? Why is that an advantage?
Okay. So I have an upcoming podcast on this very problem, but so we mentioned that for a chunk of text, you can create from that a vector that encodes the meaning. The vector is very high dimensional. So it's hundreds, maybe thousands of dimensions. You're trying to solve the problem of, given one vector, how do you find those vectors in the database that are close to that input vector? You could just run through all of them. Like you do a table scan, basically, and sort the output. And in most cases, that probably is actually fine. But if you're starting, the complexity is high enough that at scale, it's not going to perform great. So what you need is something more like a B tree lookup, which, is log in. So the vector database is actually, the vectors are probably not the important part. It's the nearest neighbor search. This is the problem we're solving, is given a vector input, what are the nearest neighbors to that vector in your database? That's the problem that you want to solve in an efficient, scalable way.
Gotcha. And so it's going through and looking at my data and saying, here are the vectors for all the parameters. And based on that, these are related words.
No, it's literally just, it doesn't look at, like, it's just given two vectors, how close are
the vectors? It doesn't know what it came from.
Exactly. Right. Now, once it finds the ones that are close, then those are in the same database row, or there's a pointer to the content that it came from, which is what you actually care about. But the database, its purpose is to do the nearest neighbor search, where you give it a vector and it finds the top K in its database that are closest to it.
Yeah. This is where I think, going back to the beginning, that AI as a product isn't something that exists. We've had fuzzy search techniques for a while. This has been something people have wanted, and everyone's gotten used to Google. I can type in whatever I want and it figures out, like you said, you take the stems of the words. And so this is another one of those, I didn't give you exactly what to ask for. So it's not a find this row in the database, but find records that are close to what I intended. And that's what you're getting to.
Yeah. So I think you might find this referred to as semantic search, or maybe neural search. The neural meaning that's how the vectors are generated from a neural network.
But it's all about that. I don't have a specific thing in mind to find the intent. I guess LLMs really fall under, in my head, the category of natural language processing, right?
Yes, exactly. Yeah.
Because that used to be a thing. Like I had data scientists on my team who were working in the field of natural language processing.
Yeah.
Is that still a thing? Is that just a subset, or has it just gotten overwhelmed in the news by LLMs?
I think you could think of an LLM as a tool to solve natural language processing problems. So, for example, I think, we used to look at things like named entity recognition, parts of speech recognition, that kind of thing. That's still something you have to do, but an LLM can do it.
Right.
And it can do it pretty well and works out of the box. If you look at what I think, again, we were talking about Google and attention is all you need. They came up with a version of that called BERT, and it would do this stuff like named entities and parts of speech, tagging, and things like that.
Gotcha. And that's one of those LLMs are these generalists, find ways to make them more specific. So if you have a specific use case in mind, you can go down a fine-tuning route. You can find a different model that's just closer. And that's going to have those benefits of it's going to cost less to run. It's probably going to give you better quality answers. It's probably going to return faster, I'm assuming, if it's less computational.
Yeah. And so this is one of the reasons people are excited about LLMs is that they are very general. That's one of the things where people started saying, is this general AI? That's been the holy grail of AI research forever. Yes, we can make a program that plays chess very well, but it can't drive a car. The holy grail is to build one model that can solve just about any problem. Just if we flatter ourselves as human beings, we can do lots of different tasks. We can do podcasts. We can, build model race cars or read books, So the holy grail of AI is, one model to rule them all. And LLMs could do so much without additional training. That's what one of the early GPT papers was. Look, we built this thing out of the box. It can do summarization, question answering, translation, code generation, all these tasks. And that's one of the things that got people really excited about it. It looks like it could do everything.
Yeah, I think it's now how do we use it? Because that seems so powerful. But going back to your point, you need to have a specific output in mind. What is your goal? Why would you add this? Because it sounds exciting. Everyone wants to use it. But do you have an intent of how does that fit into your product? How does that fit into your solution?
Yeah, it's always about what business problem am I trying to solve? And how do I know if I succeeded?
So we're way over on time. I'm going to have one last bonus round question and we'll wrap it up.
Yes.
A lot of people talk about having AI copilots. I can't remember how many Microsoft copilots and GitHub copilots and everything's a copilot. Distinguish that from an AI agent, because that's another term that's being thrown around. They both sound like the embodiment of this thing as a person. And there's a whole different discussion about that. But these are two different things. What's a copilot versus an agent?
I think we did talk about this on the Trends podcast. An agent has some degree of autonomy. The copilot is you've got to push the button to make it go eventually. And, again, I don't want to turn this into AI fear. The fear that people have of AI is autonomous AI, in my opinion. If we can mitigate that fear by keeping things as copilots, then maybe that's the way to go. But I think the key is autonomy. Like you have to agree to the copilot's answer.
Right.
And make it go.
The agents can do stuff on their own, but maybe we have supervisor agents. And like you said, I don't know how to tell the output. So I'm going to ask ChatGPT, did I train my model correctly? And you feed it back into yet another AI. The AI agent story is you have supervisor agents who watch the other ones, and then it's who's watching the watchers.
Watches the watchers. Yes, indeed.
Well, I really appreciate all your time. I learned a lot. I hope this was useful for the audience. So,
me too.
It's always good to go through and do this little refresher of here's what I think I understand, but bounce off someone who really knows. Yep. I will be sure to provide links to the things we mentioned. The eMag is great.
Yes.
And then the Trends Report and podcast and some other stuff. So, Anthony, thanks again for joining me on the InfoQ podcast.
It was a pleasure. Thanks for having me.
And we hope you'll join us again next time.